Let's figure out what the gravitational force of attraction is between the Earth and some object. So let's imagine we've got some object here, a mass, and it's being held some distance h above the Earth's surface. Let's figure out what is the gravitational force of attraction. So we know we've got some gravitational force, Fg. The magnitude of Fg, we know, is big G times m1, which we'll call the Earth, mass Earth, times m2, we'll just call that little m for the mass of our object, divided by the distance between them squared, remember, from center to center. So we're talking about this distance from the center of the Earth to the object. Well, if this object is some distance h above the surface of the Earth, and this is the radius of the Earth, then the distance from the center of the Earth to our object will be the radius of the Earth plus h. So the denominator is going to be the radius of the Earth plus h, and that quantity squared. So that's the force of attraction between the object and the Earth. I want to look at this value here. What is the radius of the Earth? Well, the radius of the Earth varies from different points on the Earth, from around the equator to the distance at the poles. It varies, but the average is usually taken to be about 6.37 times 10 to the 6th meters. Let me just write that out. So 637, that's 2, 3, 4, 5, 6 meters. Okay? So that's the radius, the average radius to 3 sig figs. What if h were 1 meter? So if I add 1 meter to that, what would we get? Well, that's not a significant figure, so we wouldn't keep that. So we would end up with the same distance. If h were 1 meter and we just added that to 6.37 times 10 to the 6 meters to the appropriate number of significant figures, that's not going to change the value. What if the distance were 10 meters? Again, that's not significant. We wouldn't change the value. What if it were 100 meters? Still no change. What if it were 1,000 meters? Still no change. If it were 10,000 meters, then yes, that would come up to 638. But what if this were, just kind of playing with numbers a little bit, 4999? Almost 5,000. If we made the argument that this were actually 5,000, we might say, okay, well, a 5 here would round that up, and we might round it up to 638. But if this were only as large as 4,999, 1 meter short than 5,000. Obviously, remember, significant figures are just kind of a rough rule of thumb as to the precision of numbers. So we're not really holding this to any definite number. But the basic idea is that h could be as large as about 5,000 meters. In other words, 5 kilometers, and adding that to the radius of the Earth, according to significant figures, would not change the value. All right, so let's just make the assumption that we are going to look at objects closer to the Earth's surface than 5 kilometers. Okay, so let's assume h is less than 5 kilometers. Remember, that's a very rough estimate. In that case, our Earth plus h is really just our Earth, and we could kind of ignore that part. So we just end up with our Earth squared. But notice, g, mass Earth, radius of the Earth squared, those are all constants, constant values. The only thing that might vary in this equation is the mass that we're looking at, this mass up here, whatever the mass of our object is. We could put whatever mass we want there, but everything else in this equation is a constant. Well, let's figure out what's the value of that g, mass Earth, over radius of the Earth squared. And what do we get? G, mass Earth, over radius of the Earth squared. That will be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the Earth. The mass of the Earth is 5.97 times 10 to the 24th kilograms, divided by the radius of the Earth, which is, on average, 6.37 times 10 to the 6th meters squared. Multiply that out, and what do we get? Can you guess? Can you guess what the answer is? The answer is 9.8 meters per second squared. It's little g. So that this force of gravity is the mass of the object times little g. Now, the fact is that if we keep 3 sig figs, it actually comes out to be 9.81. And because of the variation in the radius of the Earth, also different mass distributions, also the fact that the Earth is actually rotating, that changes the acceleration of objects down toward the center of the Earth. Because of that, this value changes depending on where you are on the Earth. Here in Atlanta, as we've said before, it's actually 9.80, but it all basically comes from this combination of constants. So what do we see? The gravitational force acting on an object, which is the mass of the object times the acceleration due to gravity, which is 9.8, or wherever you are, 9.80, times the mass. That is, what do we call that? That is the weight of the object. So, the gravitational force of attraction that we feel on any object because of the Earth is what we call our weight. All right, very, very good. Let's take a look at something else. Where do we go from here? Let's imagine that we have some mass that we throw upward with some velocity v. How high will this go before it stops? Let's see if we can figure that out. Rather than using F equals ma, let's use conservation of energy. Let's assume that it comes up to some height h. We know that the initial energy, which is kinetic, 1/2 mv squared, must equal the final energy, which is potential, which will be mgh. Divide off the m, multiply by 2, and we have that v squared equals 2gh. So no matter what velocity we put in there, we can figure out what the height is. The ball is going to, or whatever it is, the object is going to stop. But we know that that is not really the case, because as the object gets further and further from the Earth, the gravitational force decreases. It doesn't stay constant. Assuming a potential energy of this form, mgh, we can only do that if we assumed that the gravitational acceleration g was constant. But we know it's not. The farther we go above the surface of the Earth, the acceleration due to gravity decreases, so this is really not going to work out. What we need to do is try to figure out a more accurate or a correct form for the potential energy when we start getting to distances that are appreciable compared to the radius of the Earth. So let's try to do that. Let's try to figure out some potential energy that is a little more accurate. We know that the force acting on an object of mass m is going to be directed toward the Earth. In other words, we can say it's in the negative r hat direction. R hat is a different kind of unit vector. It's a unit vector that is always in the radial direction, pointing away from the origin, assuming that the origin is at the Earth. So the gravitational attraction is going to be in the negative r hat direction, always toward the Earth, with a magnitude Fg that we've already seen as g mass Earth times the mass of the object over r squared. Here we're assuming the object has a mass m. So let's see if we can't figure out what the potential energy is for this form of a force. We know that that dW will equal F dot ds. And since the force is a radial force, only displacements in the radial direction will contribute to the work. So this will be F radial times dr. So what would the total work be for a closed integral around some path that starts at some point and then comes back to that point? Well, since only the radial component of the force contributes to the work, whatever increase you have in going to a greater distance will be exactly the opposite in coming back down to the original position. So this total work will be 0. In other words, it's a conservative force. And that is going to be true for any radial forces. Any forces that have only a radial component will be conservative forces. Okay, so let's see if we can't figure out what the potential is. We know that du is equal to negative dw, which is going to be negative fr dr, which is, well, the radial component is negative fg, so minus that will be fg, so this will be g, mass Earth, mass of the object, over r squared dr. And so we can integrate and find that the potential change, in particular, from some initial to final point, so this will be u minus u naught, will be equal to the integral of g mass Earth, mass object, over r squared dr, from our initial radius to our final radius. Now, what's the integral? All of these are constants, they pull out. What's the integral of 1 over r squared? It's negative 1 over r. So this is going to be g mass Earth, mass object, over r, negative, evaluated from r naught to our r final. And let's put our initial radius at the radius of the Earth. So we're going to start out at the surface of the Earth and then go up to some final radius r. So what do we get? We'll get, this is equal to, putting in r, we'll get a negative, and then r naught, subtract that, so we'll put in r naught first, g mass Earth, mass, times 1 over r naught minus 1 over r. Okay, there we go. Very, very good. What we have in going from the surface of the Earth, in other words, at an initial radius of r Earth from the center, up to some final position at a distance r from the center, we have the change in the potential energy is equal to final minus initial, u minus u naught, which we will write as the potential at our final position r, minus the initial potential, which is the potential at the radius of the Earth, is equal to g mass Earth, mass object, times 1 over the initial radius, which is the radius of the Earth, minus 1 over the final radius r. Now let's combine these two terms. Let's put them over a common denominator of r Earth times r. So this one multiply by r over r, we'll have r, minus multiply this r Earth by over r Earth, we'll have minus r Earth. There we go. Let's factor out the r Earth. So we'll rewrite this. We have u at r minus u at r Earth is equal to g mass Earth times mass of the object over, let's factor out this r Earth. And actually let's factor out one more. So I'll make it r Earth squared and put in another factor of r Earth in the numerator. Bring out this r. And then what is r minus r Earth? R, this distance, minus r Earth would be this distance, which is what? That's the height, h, above the surface of the Earth. So this is times h, r minus r Earth. H, whatever the height is that the object is above the surface of the Earth. Okay, now what is this? G mass Earth over radius of the Earth squared. That's what we already calculated before. That is little g, the 9.8 meters per second squared. So we have m times g times h times this quantity r Earth over r. So what is this telling us? The increase in the potential energy, so this is delta U. Remember, the increase in the potential when we move from some point at the surface up to some point h above the surface is equal to mgh. But that is exactly the form of the potential energy that we were using before. But it's not the complete form, because there's also a factor of r Earth over r. When we stay close to the surface of the Earth, so that r Earth over r is approximately equal to 1, then we get a potential energy that looks like mgh. Very, very good. But what happens when we go higher? What happens when we get to such a distance that h is, or r is no longer close to the radius of the Earth, and h is an appreciable quantity compared to the radius of the Earth? Well, then what happens? Well, this term starts getting small, but this term keeps getting big. So what happens? Well, let's go back up here. Let's see what happens. Well, back here. Let's see what happens. As our final distance r starts getting very, very large, let's say towards infinity, what happens? Well, this becomes negligible, but this one stays constant. So we end up with g m Earth over radius of the Earth times m. What happens? Let's erase this and let me write that down. So as r goes to infinity, the change in the potential goes to g mass Earth, mass object, over radius of the Earth. It goes to a constant value. It does not go to infinity, as mgh would. It goes to a final, finite, constant value. Well, this is very, very interesting. If we have an object and we give it a kinetic energy, 1/2 mv squared, that's greater than that, what would happen? It would not stop. It would not go to a certain height and then fall back down. It would keep on going to infinity. Well, what's the minimum velocity that we would need in order to get the object away from the Earth and out into space, essentially infinitely far away? It would be when this quantity, 1/2 mv squared, were equal to this g mass Earth, radius of the Earth, times m. Let's do that and let's figure out what that velocity is.